variance, you see the variance function. The variance function is a function defined on the means domain. The means domain is the image set of theta nu by k prime nu. The variance function characterizes the natural exponential family. Let F1 and F2 be two natural exponential families on RD. Then VF1 M equal to VF2 M for all M in the a non-empty open subset O of the intersection, if and only if F1 equal to F2. So several classifications have been achieved in order to classify the quadratic natural exponential family, the cubic, etc. An important result here, this result shows the influence of an affinity given by this expression on the natural exponential family. So let us consider the affine transformation, where B is an element of RD and A is an element of GL of RD. So if F is a natural exponential family generated by nu, then the image of the natural exponential F is also a natural exponential family generated by phi. So is also a natural exponential family with means M phi F and its variance function given by this expression. So we can express the variance of the image of F by VF. So here Maurice in 1982 characterized the quadratic natural exponential families. He showed that there exists 6 natural exponential families with a quadratic variance function. Quadratic variance function, that is, the variance is a polynomial with degree less to 2 of 2. So up to affinity and convolution product, there are the Gaussian, which is constant, the Poisson, which is affine, gamma is given by M2, binomial, negative binomial, and hyperbolic cosinus. So we obtain 6 family. Le Tac Morat in 1990 have characterized the cubic variance functions. So they added 6 other family, which are inverse Gaussian, Russell-Candle, generalized Poisson, generalized negative binomial, strict arc sinus, large arc sinus. In multivariate case, so in 1996, Casalis characterized the quadratic natural exponential families on RD. Asari and Zerai in 26 characterizes the simple quadratic multivariate exponential families on RD. The second part so the second part of my talk is about the generalized variance. The definition, let F be a natural exponential family on RD. The generalized variance of F is given by the determinant of the covariance matrix Cas Gaunt nu theta. So the generalized variance is also the determinant of Fisher's information matrix. It is interpreted as a measure of internal variability in a population. Then it measures the dispersion of observations around the mean. Huh? Ahsari donc gave the following result. If mu is an infinitely divisible measure, then there exists a positive measure such that the generalized variance function is a Laplace transform of some measure rho nu. Generally, the generalized variance does not characterize the natural exponential family. So here, if F is a quadratic natural exponential family on RD, then the generalized variance verify the following formula, the formula given by 1. And if a natural exponential family verify the formula 1, the question, F, is it a quadratic family? So if we take alpha equal to 0 and b equal to 0, the generalized variance is constant. In this case, we show that it corresponds to Gaussian family. Of course, we have the following equivalence between the equation 1 and the equation 2. In the equation 2, if d equal to 1, we obtain v prime f mu equal alpha mu plus b. So if we integrate with respect to the mean parameter mu, we obtain a quadratic function. Okay. The example of Poisson-Gaussian family up to affinity, a random vector is called Poisson-Gaussian distributed if the first component are Poisson, the first component are Poisson, and the other components are Gaussian. Here, the matrix of the variance covariance, the variance covariance operator is a diagonal mu1, mu k, 1, 1, 1. In collaboration with Kokonenji in 26, we established the following result. Let F be an infinitely divisible natural exponential family on Rd. Assume that theta nu equal to Rd, and there exists B and C such that the generalized variance is the exponential of an affine function of theta for all theta. Then F is a Poisson-Gaussian family. In collaboration with Ghribi in 2010, we characterized the multinomial natural exponential family. The multinomial distribution is a natural extension of binomial one. So the variance function is given by the diagonal of mu minus mu transpose. If we take n equal to 1, we obtain the Bernoulli multivariate model. So if we calculate the determinant of this matrix, we obtain this equation A for n equal to 1. So here the generalized variance is the product of mu I if and only if F is a multinomial distribution or Bernoulli multivariate distribution. In 2013, we characterized the gamma Gaussian natural exponential family. So what is the gamma Gaussian? A random vector x is gamma Gaussian distributed if the first component x1 is gamma distributed and the conditional distribution of the other components given x1 is Gaussian distributed. So the variance function of this family is given by this matrix. And if you calculate the generalized variance, we obtain this formula. It depends only on the first component. Then up to affinity Fp is the gamma Gaussian model. Here, if the generalized variance is equal to this expression, then F is a gamma Gaussian model. Now, the third part is about the exponential dispersion model. So we recall the convolution product of two measures. The Laplace transform of the convolution product is the product of Laplace transforms. Here is clear. Okay. The Laplace transform of the convolution n product is n nu theta power n. So the Jorgensen set is given by the set of lambda such that L nu theta power lambda is a Laplace transform of some major ni lambda. It's clear that the Jorgensen set contains the integer set. and the Jorgensen set is closed with respect to addition, and nu is infinitely divisible if and only if the Jorgensen set equal to the open interval 0 plus infinity. It's clear that normal, gamma, inverse Gaussian are infinitely divisible, but Bernoulli are not infinitely divisible. Bernoulli, multinomial are not infinitely divisible. Yes. So here we consider two independent random variables, x and y, and the distribution of x plus y is the product convolution of the Bernoulli distribution with parameter r and gamma distribution with two parameters e and lambda. The problem is to find the Jorgensen set of the major mu, which is the product of convolution of Bernoulli and gamma. The gamma distribution is infinitely divisible. Okay, its Jorgensen set is 0 plus infinity, but the Bernoulli distribution is not infinitely divisible. Okay, we denote by R equal to R divided by 1 minus R exponential lambda, and in collaboration with Nahla bin Salah in 2011 we established the following result. If R is greater than 1, strictly R is given by this expression, then the Jorgensen set is equal to set of integers. If R is less than 1, then the Jorgensen set is equal to the interval 1 plus infinity. So if f is a natural exponential family, we have the parameter theta, and we added the second parameter, the Jorgensen parameter. So we obtain two parameters, theta and lambda. So the exponential dispersion distribution is given by this expression. Here we parameterize by the mean parameter mu. Yes. So if in the Gaussian case, a Gaussian distribution is parameterized by the mean and the variance. Okay. So here we have the mean, and the dispersion parameters is here is denoted by lambda. So the expectation of x is given by mu over lambda, and the variance of x is given by this expression. An important example of a 2D model exponential dispersion model is the 3D model. The 3D model is characterized by its unit variance, which is equal to the power of the mean parameter, where P belongs to R minus 0.1. So here the lambda equal to 1. The density function is given by this expression. So for the 3D natural exponential family, in the first case where P belongs to 1, 2, we have a compound Poisson model. If P belongs to 2 plus infinity, we obtain the positive stable model with index alpha here, which belongs to 0, 1. The third class, when P belongs to is negative, then we obtain the natural exponential family generated by the stable distribution with index alpha. Alpha belongs to 1, 2. There are some examples. Here, the variance function of the Gaussian model in the equal to 1 constant. Here, the inverse Gaussian, the mean power 3, the gamma mean 2. Okay. So the use of 3D distributions in statistical modeling was a challenging problem in the selection of the appropriate parameter P, the estimation of the parameter P, and based on a data set, making the sample relationship between mean and variance in order to generate a wide class of statistical models. So here we consider the problem of the parameters estimation. So we will estimate the parameter P by using the implicit approach, which is a Bayesian, non-informative Bayesian approach. Okay. So the general view of the implicit method, which is a Bayesian method with non-informative prior. So the implicit estimation is an alternative to estimation, to Bayesian estimation, that does not require to specify any prior distribution for the parameter. The implicit distribution is considered as a posterior of a non-parameter theta given the observed data x. So if the set integral is finite, therefore the implicit distribution of theta is given by this expression. So the sigma major, when theta is continuous, is an open interval, for example, we choose sigma as the Lebesgue major. If theta, the set of parameter theta, is countable, or we choose the countable major. If theta is the counting set union discrete sets, we take sigma the sum of the counting major and the countable major and the Lebesgue major. So the implicit estimator theta Part of theta is a base estimator with respect to the square error loss function given by the expected posterior mean, that is. So here we let y1, y2, yn be n independent observations from the 3D distributions with mean mu and variance. Then the implicit distribution of the power parameter P exists if and only if one of the following assertions holds, because there are three cases. If P is superior to 2 and mu is less to 1, the second P belongs to 1, 2. There is no condition on mu. The third case, P is negative and the mean parameter is superior, is greater to 1. So here we prove that the integral here, this integral, well, here this integral is finite of the density function with respect to P. So here, in collaboration with Hassin in 2017, we prove the existence of the implicit estimator of P. So the implicit estimator exists in these cases. And so the implicit estimator.
Sorry.
Yes.
Sorry. And if P is between 0 and 1?
P does not belong to 0, 1. Okay. There exists a natural exponential family. So there are only here three cases.
Three cases.
The first is the compound Poisson distributions. The second is stable, generated by stable. The third is also stable, but stable on R.
Okay, thank you.
Okay. So so the implicit estimator is given by this integral. Of course, in order to evaluate this integral, we need to apply a Monte Carlo method. For the regression model or the 3D regression model, which is interesting, now we recall the linear regression model that is expressed by this formula, by this linear combination. Here we add Gaussian error. In the case of 3D, the mean parameter, the expectation of the response variable, which is 3D distributed, equal to mu, and the variance equal to phi times the power function of the mean. Here, the parameter phi is the inverse of the Jorgensen parameter. Here phi equal to 1 over lambda. Okay. And so let the response variable be an independent observations from 3D distribution such that the expectation equal to mu e, and J here is the length function J of mu e equal to the linear combination of the explanatory variables xi1, xiq. Okay. Of course, when J equal to the identity, we obtain the regression linear, the Gaussian regression linear case here. Okay. So in order to estimate the coefficient of parameters beta, we use the Newton method, which is given by this expression. Here is an iterative method, and the estimator of the parameter of the dispersion parameter phi is equal to this. So here we apply the method of moments. Okay. For the beta, we apply the maximum likelihood approach. So we calculate the gradient, and so we use the Newton method. And for the parameter P, we can't use the maximum likelihood approach ni method of moments. So we use the Bayesian approach, which is the implicit approach. So we start by setting the dispersion of the power parameter to their initial values. In the TM iteration, we calculate beta in the TM iteration, and using Monte Carlo method, we calculate P, and finally you calculate the Pearson estimator of. As an example of path loss regression, path loss regression in so here we modelize the here the exact prediction is possible only of simpler cases, free space for the path loss. So the statistical estimation, the log normal shadowing model predicts the signal path loss as a function of separation using the following equation. So here y denotes the path loss, which is the logarithmic difference between the signal and the initial signal. Okay, and d is the distance between the reference. D0 is the reference distance, and d is the distance between the here donc d is the distance between the here at all. Between the reception and the emitter. Okay. So here we consider two explanatory variables, which are the distance and the quantity of obstacles x2. Okay, and we assume that y follows the 3D distribution with parameters p, mu I, and phi. And the mean here, mean of y, is the exponential of xi beta. So we assume that the rank of x equal to 3 here. So xi is the distance between the antenna and the EM position of the receiver, and xi2 is the quantity of obstacles, of obstructions between the antenna and the EM position of the receiver. So if we apply the normal model, we obtain the means, we calculate the mean squared error. And if we apply the 3D model with p equal to 1.5, we obtain a mean squared error, which is less obtained by the normal case. Okay. And here we extended this idea to machine learning model. Okay. In conclusion, the 3D regression model is a competitive with the linear regression model in terms of its statistical properties, as well as its potential for entraining entertaining wide existed phenomena and outdoor propagation signal, since in addition to its attributes cited above, it provides a superior fit to the classical normal model for modeling the propagation signal phenomena. Now we introduce the finite mixture of 3D distributions, the density given by the following sum. So here Fk is the Km3 density function, Km plus, phi k is the dispersion parameter of the Km class, and obtain of course to 1. So given by theta. The problem is to estimate the set of each observation with vector parameters p1, p2, pk. So here the problem, each observation has a label class, which is 1 or 2 or 3 or k. But the label class is a hidden variable, is not observable. So we use the expectationization algorithm in order to estimate the parameters by maximum likelihood approach. So we calculate the expectation of the log likelihood given the observation. Okay. So the EM algorithm, here we propose an extended EM algorithm. In the step initialization for the parameters, we can use, for example, the k-means in order to estimate, to obtain the initialization. The second step, we calculate the conditional we compute the posterior probability such that it belongs to the class K, to EK. And the step 3, we calculate the dispersion parameter by using method of moments and the proportion PK, and we use the stopping criterion so this algorithm converges within 10 iterations in general, okay, to obtain the convergence. In this context, we also apply the hidden the 3D model, for hidden Markov field. So we consider the pairwise ZAX is a hidden Markov field if Z is a Markov random field, and we have the joint distribution given by this product. So here we assume that the distribution of Z is given by this expression, which is the Gibbs distribution, and beta is a normalizing constant. So we apply the MM algorithm by the same way, and we study some properties, some asymptotic properties of this algorithm using this proposed model in order to identify the tumor. So is the process of partitioning digital image into multiple segments. It provides additional information about the content of an image by identifying regions .
Afif, we cannot hear you. Okay, now it's okay.
Huh?
It's okay.
So we segment the tumor class, okay, by using this model. The medical imaging techniques to compute the computed tomography, brain tumor is one of the most dangerous disease here the experimental results for the mean squared error for the proposed algorithm is equal to 2.4 for the classical HMRFM algorithm. The mean squared error is around 7.9. Thank you for your attention.
Thank you, Afif. Thank you so much. Then, are there any questions, please?
I have
Are there any?
I have a question about the algorithm that you proposed at the end of the talk. Did the probabilistic study that you present first was just to justify the results of the machine learning algorithm, or did your results improve the method?
So in the AM algorithm, we apply the AM algorithm for the 3D distribution.
There is an echo. Afif, do you have two devices that are open? Because there is an echo.
I don't understand.
Est-ce que tu as un PC et un téléphone qui sont ouverts en même temps ou pas?
Téléphone, non, c'est fermé le téléphone.
Ok, bon. Ok.
Mon téléphone est fermé, je suis dans mon bureau.
Ok, parce qu'il y avait un écho. Ok, continue, please. I'm sorry.
Okay, so we apply the AM algorithm for the 3D distribution, which have the mean parameter, the dispersion parameter, etc. Okay, but the problem is how to estimate phi. So we estimate phi by using the Pearson estimator by applying the method of moments.
Okay.
And we obtain the results. This is an iterative algorithm. So this algorithm is introduced by Dempster in 1977. Okay.
Okay. Okay, thank you.
Thank you.
Wissam.
Are there any questions, please? Afif, could you please go to slide number 23?
23.
3.
Huh?
Above, go backward, please. 22, maybe. 21, then. Sorry, then it is in 25 or 26.
21.
Sorry,
Huh?
25, maybe.
20?
Sorry. If you go forward,
25.
24, then.
6.
No, 24.
4.
Perfect,
Yes.
perfect. Okay. Maybe, I'm not sure, but in the third case, the power of lambda there normally is negative, the exponent of lambda. No?
lambda.
You have a density in lambda or in y?
Yes, 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 yes. Yes, the lambda is positive, the lambda.
No, but these are PDF, right? PDF in y, no? These are expression of PDF in y.
In PDF, yes, is the generator measure. The generator, the generator, yes. The stable distribution, the density of the stable distribution.
If I understood well, these are of probability density function.
This density is given by in the book of Feller, for example, Feller.
Or Pleterev.
Feller.
The second and the third expressions are expressions of probability density function in y, right?
Yes, but the sum is 1 to infinity.
Understood. But can you confirm that the function Cp of y is a PDF?
Yes.
Okay, then the third expression, the exponent of y should be negative.
Negative.
Okay,
maybe,
just check this. Could you please go?
Maybe there is a mistake. Maybe, but we have yes, it exists in Feller. On we change minus y by absolute value. I don't know exactly. Maybe there is a mistake.
And can you please go forward page 20, maybe 27, sorry. Okay, could you explain, you see where is the cursor, the hand? There is a symbol P with a double bar. What do you mean by the symbol?
Symbol what? The likelihood function. The likelihood function.
You denoted it by P.
Okay, the density function of the observation given the theta parameter. In general. Yes.
Thank you. Okay, understood.
Okay.
Thank you.
Thank you.
Are there any other questions, please? So if there are no other questions, I would like to, on behalf of the group, to thank Afif for his nice and clear talk, and hopefully we'll meet soon and attend to one of his talk in person.
Thank you, Afif, for accepting the invitation. And I make a reminder that November 8th, Sébastien Tordeux from Pau University will give us a talk. Thank you very much for attending this webinar. Goodbye.
Goodbye.
Bye. Goodbye.
Merci, Afif.
Stop the recorder, Nabila.
Okay.